logic, because oh yes. Okay, that's how we normally. Huh? Thank you.
With analysis sequence, usually. Well, I mean, the goal is not to teach them formatting.
Anything to a letter. That's unusual at the blackboard.
I won't be this careful.
These will be a tool for that. And so we will do like another process that like for specifically.
So, it looks like we've reached a critical mass. The only announcement maybe today is if I'm late with ringing the bell, feel free to take over the burden. My PhD students actually, I have for my work group, I have a big nice gong, and my students always compete for who can bang the gong. And so if you're like that, the bell is over there.
Talk a bit more until I finish writing.
Oh, yes, I have an announcement as well. Unfortunately, we didn't manage to bring you the weather we had planned. But this is Germany, so...
Okay.
Good. Oh yes, and we have now all the consents of all the speakers and almost all the slides. So we should have the school videos really up. And for all the speakers who have slides, you need to give your consent and you need to send the slides. But they should have pinged you for that before your talk.
No.
Mm-hmm.
They ping you after the talk, usually.
Okay, good.
Okay.
I told them, I asked them to do it
Is
before.
giving consent a formal thing?
Yes, you have to say yes,
Oh, okay.
so that they can publish your
Send you an
video.
email and then you say yes.
Okay. Okay.
Literally.
Let's start.
Yes, please.
So, hi. Thank you for the opportunity of talking about my research here. Actually, I think I never really told anyone many details about what I'm doing here this month. But since the month is getting to an end and I'm leaving, I thought about like telling you what I'm doing, what I've been thinking, and what's the state of all of this as of the end of this month, or more than a month-long stay in Bonn. I work in a topic that's not so common, and so for a long time I had trouble telling people exactly what I work with. Like you ask a mathematician and you hope to hear something like, I'm a geometer, like I work with whatever manifolds, Aristotelian manifolds, whatever. But that's not what I do. I like to think about mathematics from meta level, one that even in logic is not so common. And I finally figured out that what I'm working with is methodology of mathematics. That may sound kind of innocuous, but it's not a common thing. In my experience, I have never seen like mathematicians seriously discussing the methods behind their work. We usually just do the work. I think part of it has to do with the fact that we can provide proofs for our results, so we don't really need to like talk about how we got to them. unless we are talking in an educational sense. But anyway, you would imagine that like a physicist that did an experiment, it's important to understand how the experiment works. But that's not the case in mathematics. But I like to think about how things work. After all, I went into logic. I like to think about how thought works. And I like computer science because I like to think about how machines or calculations or algorithms work. And so I ended up thinking about how do I do mathematical research. Part of this has to do with like having strong opinions about what is good and bad mathematics and trying to make that into something serious which I can defend. Turns out you need like a PhD to really formulate an argument, and not even a good one, but anyway. What is methodology? Methodology is the study of methods, right? There are two parts to this. One of the sides of a methodology is, let's say, the goal, the underlying goal. If you talk about methodology of something, that something is usually an activity which has a goal. I'll talk about, well, in our case, the goal is doing mathematics. And that's not a clear concept, what doing mathematics means. So I have some working definition, has to do with the way I particularly do mathematics and engage with concepts. On the one hand, I would say that we are concerned about theories. Has anyone here ever heard this term? Theory building? There's a text by, I forget his name, called The Two Cultures of Mathematics. I have all the references in the slides that I'll share. Who is it?
Tim Howard.
Yes. There he presents this idea that
Jim was already using one called the CP Snow, you know, the guy who originally came up with.
yeah, he talks about the two cultures of the humanity. But I'm borrowing this idea of like there's basically two styles of mathematician. There are those that are concerned with solving problems. There are the problem solvers, and there are those that are concerned with building theories, the theory builders. Right? It has to do with the priorities the mathematicians set for themselves. What moves their, what interests them, right? There's, in this text, there's a passage about a quote from Atiyah, where someone asks him, how do you choose a problem to solve? And he responds saying, actually, I think the question is misguided. He has an implicit assumption. I don't choose the problems. I simply engage with mathematics. I explore concepts. I talk about things, and the problems that actually come up in that discussion. So a theory builder solves problems, but in the interest of understanding a larger theory. While, for example, in the text, it gives the example of Paul Erdős, who is the archetypical problem solver. He was interested in problems, and the theory that comes out is just like with the purpose of better solving problems. So that's the kind of style of mathematics that I'm concerned with. Besides, I'm thinking of mathematics not in that static sense. There's a philosopher, Chilean philosopher called Zalamea. Is he Chilean or
Sorry?
Colombian? I think it's Colombian. Anyway, Fernando Zalamea, he presents in several ways the critique of like the philosophy of mathematics, which he says is not really concerned with mathematics at all. He actually says that the so-called analytical philosophy, he calls it Anglo-Saxon philosophy of language and whatever. Because what he's getting at is this idea that to think about mathematics, about the philosophy of mathematics, you have actually to engage with mathematical concepts, and now I'm putting in my interpretation, you have to engage with the crude reality, which is that mathematics is made by humans, for humans. It's, after all, a human practice. And these views are well articulated in a text by, I forgot to write down my references. Anyway, it's called Narrative and the Practice of Mathematics. It's from a book called Circles Disturbed, which I recommend. It's a book on talking about the relationship between the narrative and mathematics. And in this text, the author presents this idea that, bringing from another author in ethics, and he's talking about how mathematics works as craft, right? You have, the professionals are engaged in this sort of building of, not material, but things, and we have standards of how we build those things, and we have narratives about how we build those things. And when you insert yourself inside of this craft, of this trade, you build a narrative on how your work fits within the history of that field. And so this will all become relevant. I'm talking about a bunch of abstract things, but I'll give some examples later. Okay. Okay. The second part of our methodology is the methods themselves, so the how. How do we do what we do? And now it's the part where my own personal vision comes in. My goal is to develop a particular kind of methodology of mathematics, using some techniques. My own point of view is that coming from logic. So I like to think about logic as a... I like to investigate logic as a way of doing mathematics. This is not so obvious. What is logic? In the larger sense, it's about encoding knowledge and reasoning in formal ways. And it's not so trivial to think about how to do mathematics with that. Actually, in this room, maybe it's trivial because, like, formalization is all about that. We formalize mathematical knowledge, but the point is, how can formalization actually help us develop new concepts instead of just recording the concepts that we already have? In particular, I like the idea that mathematical knowledge and knowledge in general can be thought of as a modular system. Has anyone here heard of Christopher Alexander? Yeah? For those that haven't, have you heard of pattern languages? Or even programming patterns that everyone knows? Christopher Alexander was an architect, and he wrote a lot about the theory of design, let's say, depends on how you wish to classify his work, but philosophy of design. He worked on the methodology of design, so to speak. And he introduced this idea of pattern languages, where he was talking about how in the modern world we deal with complex problems which do not easily fit in our heads. And moreover, when we are dealing with problems which have several dependent variables, the space of possibilities is so large that the only possible way of dealing with such problems is to subdivide them into smaller systems which are more or less independent of each other. In programming, I guess, we do that with like object-oriented programming. You have the programming patterns. It's the idea that you take a program, a huge complex thing, and you divide it up into smaller bits that have particular behaviors and interact through well-defined interfaces and borders. So this is the idea of modularity. And in mathematics, the sort of thing that implements modularity is, for example, MMT. So my co-student, Florian Rabe, works with a system called MMT, which I think is like a really good example of how you can talk about modularity in mathematics. The idea that you can write mathematical knowledge in little theories and relate them via morphisms. The flexi-formalist view of this is using, for example, Esther and dividing things into little modules. And I'll get into how concretely this comes up in research. So anyway, let's go to an example. Because one of the other important questions about methodology, actually, is that there is another level to this. Which is, how do you actually develop a methodology? Methodology is the study of methods, so what is the method for doing that? And I didn't come up with a better answer than just doing it. But I have a fancy words to say that. It's praxis. So the idea is that we can reach a better level of understanding of our own craft if we do it and think about it, and do it and think about it in a dialectical way that sublates into the idea of praxis. So this is a fancy way of saying that I chose to work on a case study, which I'll present, and later I thought about thinking about what I did and coming up with a description. Just in the same way as you start programming in an unstructured language and then you figure out that, oh, look, we are doing this kind of loop all the time, so perhaps we should add a construct or a language that does this. Oh, look, we are encapsulating data and behavior and whatever, so let's make that into a language feature, etc. So what is the case study? I bet you all heard of algebra, right? There's a field called universal algebra, which is a formalism for describing all of the usual constructions, common constructions in all areas of algebra in a uniform way. And one of the primary theorems in that, or let's say one of the important theorems in that area is called Birkhoff's HSP theorem. So let's do a quick guided tour of that theorem, using some definitions and try to give you an idea of how it's proven. So, first of all, a signature is just a type and a narrative function. This encodes the operations that you have and how many arguments does it get. It's not dependent, it's just type. So an algebra is given by a type and an interpretation function that gets an operation and gives you a real concrete operation on that type. I'm going to breeze through the first definition because I think everyone is familiar, but if you have any questions, please stop me. Terms. a term on n variables is either, well, a variable, xi, or c applied to I terms. Well, yeah, to the arity of C terms. That's a term.
Can you break the... Thank you.
By the way, I'm doing this so we can compare to what I'm doing later. I need to have this whole thing written. The interpretation of terms is done in the usual way. We say that xi interpreted in an algebra A is just the ith projection, and C of Tii interpreted in A is simply Ca, which is just how I write the evaluation, applied to Tia. Right? And evidently we say that an algebra, here is an important thing when you're talking about the HSP theory. When you're talking about algebra, you can have several different logics for it. The most basic kind of algebraic logic is equational logic, where you deal exclusively with equations. There are some structures which you cannot axiomatize using only equations. For example, fields, right? How do you know that fields are not axiomatizable only with equations? The answer is using Birkhoff's HSP theory. We'll get to it. We say that an algebra satisfies an equation if and only if I'm abusing notation. This should be a composition. I'm interpreting terms as functions, just to avoid variable assignment and whatever. So if TA is equal to UA. And as all mathematical structures go, we have morphisms between algebras. A morphism between an algebra A and an algebra B is a function between the elements of A and the elements of B, such that f of, for all C of operations C and elements A, CA of AI is equal to CB of f of AI. Now we define two kinds of transformations between algebras and sets of equations. We say that theories varieties. We say that the theory of an algebra is the set of all equations that it satisfies. Okay? And the model of, let's say, a class of algebras. And the model of a set of equations is the set of algebras such that it satisfies all of the equations in the theory. Okay? This is the usual notion of model and theory. Now, given a theory, we want to, one of the things we do in algebra is that having a structure, and if we want to impose certain other conditions on that structure, we have a way of transforming that algebra into an algebra that satisfies the other structure. That's called a quotient, right? To do a quotient, we quotient by some congruence. So we define the congruence of a theory T as saying that A is related by T to another term if and only if there exists TU terms such that there exists A0, let's say, A0, the same number of arguments in both of them, such that T A of A0, AI, let's say, is equal to A UA of AI is equal to A prime, and T U is in the theory. The details, I don't think matter that much. And then we have a bunch of results which are expected until we get to the final big theory. So here, there are three algebras. I'm presuming that everyone here knows how to build a free algebra. Theorem. Every algebra is a quotient of a free algebra. Right? This is not obvious. Think about it. It's actually a funny thing for our logic to do. The fact that you have theories, you have a bunch of axioms, and you have a model of those axioms, and now you add a bunch more axioms, and you can find a model of the expanded thing, as long as it's not trivial. Like, it's unusual. Think about it if you were like first order logic. It's a difficult thing to do. In algebra, we can do it. It's kind of magical. Then we have an important lemma that I'll show later how it comes up, that says that the free algebras in a variety, which is the collection of models of some theory, is a subdirect product It doesn't matter what that means. It only matters that it has to do with products and subobjects, okay? Of some generators on the variety, or of the objects of the variety. And then we get to the big thing. A class C of algebras is a variety. It's characterizable by a set of equations if and only if it is closed under products, quotients, and subobjects. Is this new to anyone here? Okay. Everyone knows here about Victor. I think it's an elegant statement. It's short, but it's very powerful, right? Think about it like this. To show that fields are not axiomatizable by equations, it's enough to show that they are not closed under products, quotients, and subobjects. Yes?
So is the variety here at all related to the geometric variety?
No.
Completely different.
Not completely different thing. I mean,
Just overloaded?
and I thought yesterday about if someone was going to ask me this. No, they are not. I mean, as far as I know, they're completely different concepts. So, perhaps someone can somehow relate them, but that's just a coincidence. Different things. I don't know why they call it a variety. That's a 30s thing. Like Bukov was writing this in the 30s, and I think it's like a variety. They use that term because perhaps set, sort, type, they were all taken, you know? So it's just a variety of objects. Like, for example, groups. You can axiomatize groups via equations, right? We give a signature and we have just obviously the equations are universally quantified, but that's implicit in my interpretation. So you take fields, for example, they are not closed under this three things, so they are not axiomatizable via equations. That's simple, right? You turn a hard statement, it has to do with like swapping quantifiers around, right? Here you have to show that of all the possible axiomatizations, none of them pick out the fields. And here you just have to find some fields for which the closure relationship fails, right? So this is an important theorem, but I'm not interested in its applications. I'm interested in the technique. There is something which people like completely deranged mathematicians invented in the last decades, which is called multi-algebra. So the idea is, what if, like, when you add two numbers, you didn't get just one result? You get more than one result. So the changing definition is actually simple. You just change that's it, right? Now every algebra has a multi-operation as the interpretation of its symbol. So it should be easy, right, to just propagate this change until we get to the theorem, right? But that's not how it works, obviously. The thing gets messy really quick, and it's hard. And people thought, kind of like had this feeling that you can't do this proof of Birchhoff's theorem for multi-algebras, because there is a result saying that the functor, the forgetful functor that picks out the base of the multi-algebra, has no left adjoint. So there are no free multi-algebras in the traditional sense, categorical sense. But this is one of those situations where category theory actually fails you. Because category theory is one of those, there's a book called Tool and Object. It's a book on the history of category theory. And there's this idea that category theory can be approached as both a theory and a language. When you study as a theory, you are interested in the categories themselves and how they behave, how they interact, and whatever. But many mathematicians, me included, use category theory in another sense, as a method of structuring thought and guiding questions and lead you into what kinds of things you should do. So if you make a construction that's not functorial, you usually think, well, I think this is not correct, right? And if you indeed can compute categorical things out of your definitions, you think that it's correct. But in this case, it fails you because, I'm loading the way I'm saying this, but it's actually that we tend to think that free algebras mean being the image of an adjoint and whatever. But in this case, this is an instance of what Mario said he likes to call trivial generalization. In the sense that the theorem, Birkhoff's theorem, doesn't actually use the fact that there is an adjoint function. It uses much less than that. Here's kind of where I think proof assistants start getting into the picture. Dependency analysis. This is the kind of thing where like a proof assistant is really good at looking at the dependencies, the inferences, and telling you what exactly you are and are not using, right? So, let me give you an idea of after like 2 years, we got into the following formulation. This is much shorter, okay? An institution, which is something that exists in the literature, is given by a category C of signatures, a functor of sentences, a functor of models, or rather structures, and a satisfaction relation that satisfies a particular axiom. Right? In an institution, we can define the same thing as the theories and varieties. Right? You have given a signature, you have a set of sentences, you have a category of models, and you can define the models that satisfy a particular set of sentences and the set of sentences that satisfy a particular subcategory of structure, so that works. But we don't have the machinery to talk about quotients. So here's where we came up with another definition of what is called an extender. So an extender is a pseudo-functorial section of model. What does that mean? Given two theories, T0 and T1, and let's say T2, we have a function from x, T0, T1. From the models of T0 to the models of T1. In such a way that the extender, like extending a theory to its own theory, is equivalent to the identity. This is the pseudo, or perhaps I should say weakly, functorial, and T0, T1, T2, T1, T0 is equivalent to, right? Quotienting by something, and quotienting again is just quotienting by the larger thing, or isomorphic. That's important. I'm not using univalence. Then we say that an extender is complete if the essential image of the free algebras or structures, object, let's say, is the column A. Oh, what are free structures? Well, free structures are just things for which, like, F is free for T if the theory of F is T. And that's it. Exactly T, not that it satisfies T. This is exactly what a free structure in algebra is. It's the thing or an absolutely free structure is something which satisfies exactly the theorems. Or in the case of algebra, it's just like the trivial equations. Everything is just equal to them, to itself, and you don't have any identification between terms. Then you have compatible closure operators, which satisfy this condition. The extension of some structure from a theory to an intersection of theories belongs to the closure of the extensions to the particular theories. What does this mean? Well, it doesn't matter. The thing is, remember that I told you about like the where is it? Subdirect products, right? Something has to do with sub-objects and products. And you can build the free structures using products and sub-objects. Well, this is encapsulated in this P. The idea that you can take an extension to a, let's say, the intersection of the theories of a bunch of things, and you can build them through, via these constructions from the extensions in the lower theories themselves, or the, let's say, larger theories. And out of this, I can actually prove the Birkhoff theorem in this very enlarged environment. And the proof is very similar. I never told you the proof, right? So, why do you need all of these ingredients? The idea is that let's do an illustration instead of proving. You have a class of structures, C, right? It doesn't need to satisfy anything. And then you define, you look at the variety of C generated by C is like the set of all structures that satisfy the equation satisfied by this. It's the smallest variety that contains a class. And you have the closure by products, subobjects, and homeomorphic images, HSP. Right? And the way we show these two are equal is by showing that we can actually find the free structures in this, in the variety. They are built from the elements of this. And since every structure in the variety is a quotient of some free structure, we get that, and obviously by definition this is constructed via HSP, right? We close the circle and now we have the proof that those two classes are equal. And these definitions, these abstract definitions, although they seem like abstract, in fact they are exactly the ingredients that you use in the traditional proof to prove the theorem. So this is, in my sense, a trivial generalization. I'm just tossing away assumptions that I don't need. I don't need to assume that the algebras are sets. I don't need to assume that the theories are made of equations. I don't need to assume that I can build quotients in this particular way, that the operators are products and whatever. Now, you might object that this proof actually has a bunch of, let's say, holes, which I carefully make into parameters, so that the compiler doesn't complain. For example, I have the extender. This is a hole. Compatible closure operator. This is a hole. The fact that the extender is complete. What else? There's a bunch of things. The institution itself is a whole. It's a parameter, right? And to recover the proof of, like in the traditional case for algebra, you just plug in the values for those parameters. So you build an institution for algebras. You provide an extender that's given via the quotient. You prove that it's complete. You prove that the product and subobject closure operator is compatible, and you get your theorem for free. But actually not for free, right? Because you did a lot of work and it's for nothing, right? No, because now what we can do is take this and apply it. It gives us a template for proving this in another setting, for example, the setting of multi-algebras. So I'll fit the whole all that we have about multi-algebras in this little square so far. Let's say truth is we don't have much. We have been working tirelessly through into plugging these holes, and we have been making steps. It has something to do with because you can't quotient because operations give sets of results, so that messes up a bit the quotients, and instead of looking at the elements and having like equivalence classes, we want to look at the classes of subsets and etc. And you don't actually work in the category of like algebras, you work in the Markov, in the Kleisli category of a monad over a Markov category enriched over graphs and blah 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 blah. This is just a bunch of parameters which are actually telling us a lot about what is happening in multi-algebra. I'm not gonna talk about this because like time, but the point is that this process tells us a lot. And let me sketch some of my conclusions. So the final question is, what is it that we are doing when we do this kind of generalization? Right? The whole point is to identify certain patterns. And we have identified some patterns. And the kind of the ultimate goal that I have is to build a kind of a library of programming patterns for mathematical research. So I have seen some books in object-oriented programming that have like the illustrations and the little cards that say like name of the pattern, purpose, structure, whatever. And we can actually start filling this. For example, here is common. Is this common? How do I spell common? Common abstraction. Purpose. Transferring proofs to formally similar domains. Structure. 1. Unravel original theory. This is another pattern. 2. Guided parameter discovery. Guided parameter discovery. 3. Parameter determination. So I'll close with 2 things. First is that we intend to put this methodology to the test by having other case studies which look like they could benefit from a formal treatment and apply those recipes to that area and see what happens. But let me talk a bit about this pattern and why this illustrates a lot of what I think formal methods in the sense of like proof assistance can contribute to what we're doing. So, unraveling a theory, what does that mean? That basically means to take a bunch of entangled concepts, such as, for example, the proof of Birch's theorem, and literally pull its strands apart to see what structures play a part in that proof. So we actually find that definition by unraveling this. So we see that the signature, the algebras, the terms, the interpretation, and the morphisms, they just give you an institution, and that's the pattern. You can make a cut right there and say, this is a clean interface. From that, you can import some notions from institutions, which are, for example, the ideas of theories and varieties. And then you can bring in from another different theory, the ideas of congruences and how you can like relate things and work with sets and whatever. And the whole thing, you can actually see that the particular steps that you take in the proof, they are each a little tool that comes from a different toolbox. And unraveling has to do with this. So one of the things that I've been doing this month is actually writing these proofs and definitions in Nasdaq and using it to like look at the theory graph. Could I do it manually? Yes, but it's much easier if like I have a thing that complains when symbols are not defined. You start writing the proof and marking the symbols and it complains to you, look, this notion is not defined, and then you do it again and you're doing different modules and it tells you which module needs to import what, and you end up with this graph of concepts. Now, having the graph of concepts, you can actually go and pick apart like the things that you don't need. This is the trivial abstraction. It's another thing that proof assistants are good at. Then there is this, the guided parameter discovery. Another pattern which I would say is like, there's something in functional, in analysis, like solving partial differential equations, they call variation of parameters. Sometimes it's easier to solve a particular equation if you put another parameter there, because then you have like a bit of leeway. And this is kind of what we're doing, right? The institution, the extender, the compatible operators, those are all parameters that are filled. You think of it like a telescope, in a sense, that's of definitions which are filled in order to get the original theory. But then you can fill it with other parameters, which is the third step, to get to the place where we are trying to get. So, I know it's kind of confusing, it's a lot, and it's not very clear. Like, I don't have a proof assistant to show you, I don't have like a computer program running to show you the results, but this is kind of the mind map of where I am and where I intend to go, and hopefully by the start of next year I'll have like something written to show you. And yeah, that's it.
Any questions?